General steps of finite element method. In the previous lecture, we learned what is finite element method, what are the applications of finite element method, how the finite element method works. Now, in this class, how the finite element method procedure to solve any physical problem or any engineering or mathematical problems. The fundamental concept of this finite element method is continuous function of continuum having infinite degrees of freedom is replaced by a discrete model, means and approximated by a set of piecewise continuous function having finite degrees of freedom. This is the basic concept of this finite element method. Now, in this finite element method, it follows a sequence of steps or general procedure if you want to solve any problem. So first, discretization, selection of approximate function, and what is the relation between the strain displacement, stress strains, and formulation of the element stiffness matrix and formulation of the total stiffness matrix and total loading matrix, and calculate the unknowns or simply modal displacements, and finally find out what is the stress and strains of particular elements and interpret the results. These are the sequence of steps if you want to solve any finite element. First step is discretization. In this discretization or selection of an element, it involves dividing the domain or body into equivalent system of finite elements with associate nodes and approximate element types model that is most closely to the actual physical behavior of this component. The node numbers, the element numbers and the type, what is the type of the element and size of the element and arrangement of the elements are to be decided in this discretization process. So we may understand here, this one is domain. So the domain has been divided into a small number of pieces, or simply you can do the meshing. So here, for understanding purpose, a 4-noded element is considered for in 2-dimensional cases. So this is the generation of mesh domain into finite element mesh. Now, like that, we have to identify whether it is 1-dimensional element, 2-dimensional, 3-dimensional, which element is suitable to solve this particular problem. We have to identify. And suppose we may choose 1-dimensional element. In this case, simply bar element or 2-noded element are available, and 3-noded element. In 2-dimensional case, that is triangular element, quadrilateral element like 3-noded and 4-noded. If you go for higher order, 6-noded and 8-noded. What is higher order? What is lower order? We will learn in the next classes. At the same time, in 3-dimensional case also, tetrahedron, hexahedron, pentahedron elements like 4-noded, 8-noded, and 6-noded elements are there. We have to use these elements and develop the relation or find out the interpolation function for this element. Next step is selection of displacement function or interpolation function. In this, it defines within the element using nodal values of the element like linear, quadratic, cubic, polynomial. Most of the cases, polynomial equations are frequently used because they are very simple to work with the finite elements. and at the same time formulating is also very easy. So the FEM, this finite element method, is on which the continuous quantities such as displacement throughout the body is approximated by its discretization. So it is composed of a set of piecewise continuous functions defined with finite element domain or finite element. So for simple to understand, we see that the polynomial equation might be a constant, linear, quadratic, and cubic, like that. In this case, suppose u is the displacement, you may consider the linear case. U is equal to 2x plus 1. The 2 and 1 are the constants. In case of two-dimensional case, we may choose this Pascal's triangle. Suppose its polynomial degree is 1 and polynomial degree is 2, 3. According to the polynomial terms or number of nodes, we may choose the particular polynomial equation to derive its shape functions. So for simple to understand, easy to understand, first we assume a bar element, it has two nodes. This one is here is node 1, another one node 2. So u1 and u2 are the displacements at node 1 and node 2. F1 and F2 are the forces at node 1 and node 2. The length of this element is L. In this case, because it has a two-noded element, at the same time it is a one-dimensional bar element, so we may go for the polynomial equations with one dimension, means x only we will consider. U is equal to a0 plus a1 x. Here a1 and a1 are the constants. So these a1 and a1 are found out by substituting its boundary conditions of this element. This is the selection of interpolation function for the particular element. The third step is define what is the relation between strain, displacement, and stress strain relations. These relationships are necessary for deriving the equation of each element. Suppose in one-dimensional case, strain at any point, strain in x direction is equal to dou u by dou x. Simple things we know from the mechanics of materials. We can say mechanics of solid subject. We know that this dou u by dou x, change in length by original length, that is called the strain. So at the same time, stress at any point in one-dimensional case is equal to, say, stress x direction is equal to E into strain. Here, what is capital E? It is an Young's modulus, it is a material constant. So similarly, we may go for two-dimensional case. Stress at any point in 2D is given by strain in x direction is equal to dou u by dou x, and strain in y direction is equal to dou v by dou y, and shear strain is dou v by dou x and dou u by dou y. All these things we know that from the mechanics of solids. And similarly, stress at any point in the stress in the matrix equation in the matrix form, stress in x direction, stress in y direction, shear stress in xy. So E by 1 minus mu square, and this